Section 25.5 UV-Vis light absorption in polyatomic molecules. Most UV-Vis spectra are not vibrationally resolved. So that means you will not be able to identify a sharp peak that corresponds to a certain vibrational transition from a certain vibrational quantum number to another vibrational quantum number. Why is that? There are three reasons. Reason 1, an atom does not vibrate. A diatomic molecule has one vibrational mode. And then you can observe different transitions from the ground vibrational state to the ground first excited, second excited, third excited, fourth excited, etc. vibrational states in the first excited electronic state. So you can observe multiple peaks in the electronic transition of a diatomic molecule. But when you have a polyatomic molecule, such as water, you have three vibrational modes. Ammonia has 6 vibrational modes. The electronic transition of ammonia may be accompanied by 6 different types of vibrational excitations and even de-excitations of the vibrational energy levels. So for each type, you may observe 0 to 1 vibrational transition, 0 to 2 vibrational transition, etc., etc. And sometimes when you have the molecule under high temperature environment, you may also observe the de-excitation of certain vibrational modes. So that makes the UV-Vis light absorption really complicated. So now I'm going to show you 3 pictures. They are the UV-Vis spectra of an atom, a diatomic molecule, and a polyatomic molecule. So this is the UV-Vis of an atom in the gas phase. This is really sharp because this electronic transition is not accompanied by any vibrational transition. This is the UV-Vis spectrum of a diatomic molecule. And you may observe this electronic transition being accompanied by vibrational transitions. Over here, this is a polyatomic molecule with many different vibrational modes. So that's why this UV-Vis spectrum is not vibrationally resolved. You cannot see any sharp peaks because there might be hundreds of different peaks overlapping each other. The second reason, this is from the Heisenberg uncertainty principle. The line width of each transition is broadened due to the very short lifetime of the excited state. This is a different form of Heisenberg's uncertainty principle. So if you have a very short time period, you will have a very large uncertainty of energy for this excited state. So the uncertainty of energy times the time period of the energy measurement is greater than 1/2 h bar, and h bar is the Planck constant. So if delta t is 10 to the power of negative 13 second, and h bar is roughly 10 to the power of negative 34, that means your delta E will be as large as 10 to the power of negative 21 joule. Actually, that's a very large uncertainty because 10 to the power of negative 21 joule can be converted to 100 joule per mole. So it's not negligible. The third reason why the UV-Vis spectrum are often not vibrationally resolved. So like this, you cannot see individual sharp peaks. Reason 3, each molecule may be in a different chemical environment, especially if you are taking the UV-Vis spectrum of a liquid sample or a solid sample or a solution. In those cases, the chemical surroundings for each molecule is different, and therefore you will have different energies of the ground state and the excited state for every single molecule, and that will make your peaks broader. If you want to get sharp peaks for a diatomic molecule, it's better to do that in the gas phase with an extremely low pressure.